An OpAmp-based active circuit realization of first-order low-pass Butterworth filter is shown here. Let's figure out how to find and compute the transfer function and frequency response of the system. Okay, so what we have is the input Vn, as you can see, and then there is the first OpAmp, ideal OpAmp, with positive terminal grounded and a negative feedback mode. And we are assuming OpAmp is not saturated. It's the ideal OpAmp, so input impedances are infinite. And the same thing about the two other OpAmps as well. So they are ideal OpAmps with positive terminal connected to ground, and they are in negative feedback mode, and they're not saturated. So with that assumption in mind, let's start with the output node. So output node is Vout. Okay. We know this is an ideal op-amp, not saturated, and active op-amp. So assuming the negative feedback is functional, therefore we know that the voltage at negative terminal should be matched with the voltage at positive terminal, which is grounded. So the voltage here should be zero as well. Therefore, what happens is whatever current flows this way, since it can't go inside op-amp because input impedance is infinity, it has to flow through the capacitors C as well. And of course, we know that the impedance for cap is 1 over Cs, and so that is X of C, and then the impedance for resistor is R2 unknown. And the output voltage is VOS. That's what we know. Okay, so with that in mind, we can just write down a simple KCL here, and you can figure out the Vx as a function of Vout. So we can say Vx minus 0, that's the voltage at this node, divided by R2, divided by R2, okay, is equal to 0 minus Vout divided by 1 over Cs, which is Cs times, let's just do it this way, which is 0 minus V out as a function of S, and then times Cs. Okay, so from here it's obvious to conclude that Vx is just equal to minus R2 Cs times V out. So let's highlight this as equation 1 because we're going to use it. Okay, so this is my equation number 1, and I'm going to use it. Okay, so we know Vx as a function of Vout. Now, let's follow this feedback route here. So it's an ideal op-amp, and we know it's in negative feedback loop, not saturated. So whatever voltage appears here, the voltage appear at Vy is just minus R divided by R times this voltage. So Vy, I mean, you can just again write the same KCL idea. So here is 0 volt, here is 0. So whatever current flows this way, there is no way for that current to go except flowing this way as well. So if you write a KCL, you will end up with figuring out Vy is equal to minus R divided by R. So it's going to be negative R divided by R times V out. So from here, it's easy to conclude that Vy is just equal to negative V out. Okay, so that's our second equation. Okay, so we now Vy, we now Vx, both as functions of Vo or Vout, and then therefore at this node we can just simply write KCL and be done with the whole thing. So for the same reason the voltage is 0 here, and then the voltage here is also forced to be 0 at negative terminal, assuming this op-amp is not saturated. And in operational mode, in a negative feedback scenario, that's how the equal voltage at the both input terminal enforced. So as a result of that, we can just write that whatever current that is flowing this way should be equal to the sum of these two currents, this current plus this current. And to do that, just write a simple KCL at this node. So if you do that, writing KCL, same as before, you would get Vn minus 0 divided by this resistor R is equal to 0 minus Vx, so 0 minus Vx divided by resistor R, and plus 0 minus Vy divided by resistor R. So the nice thing is these resistors are cancelled out from each other, so we get Vi is equal to simply minus Vx minus Vy. And we're going to substitute using equation 1 and 2. So using these equations, 1 and 2, we're going to get Vi or Vn is equal to negative Vx, which is R2CS V out, plus Vy minus Vy is just V out, and that's 1 times V out. Okay, so as a result of this, what we get is Vo, of course, Vo of S divided by V in of S, or just VIS, just to keep it simple. Okay, is equal to just 1 over R2CS plus 1, which we can further just divide both numerator and denominator with 1 over R2CS. We get 1 over R2CS plus 1 over R2C. So this is the transfer function that we were looking for this first order Butterworth filter. So effectively this is our H of S, and with this we conclude that the cutoff frequency or omega C is just simply equal to 1 over R2C. Okay, so what is the consequence of this? For example, let's say you want this cutoff frequency. Okay, so that is the 3 dB cutoff frequency. So by that, what I mean is, if I show the hypothetical magnitude response, you would get the response of this low-pass filter something like, okay, so you would get the response of this low-pass filter something like this, if this is frequency, let's say, and this is just magnitude response flat. Let's say when S is equal to 0 at super low frequencies, then it's just a transfer function, or the system response is 1, so you get 0 dB. That's 1, or 20 log 1 is 0 dB. And then when you get to okay, when you get to at around let's say omega C, or your cutoff frequency, which is 1 over R2C, the drop is 3 dB magnitude drop. So here at this point, you're dealing with negative 3 dB, or basically power is divided by 2. So output has the half of the power of input at that point. And then after that, we have a drop of 20 dB per decade. Decade meaning after this point, roughly after the omega C, every 10 times every 10 times increase in frequency result in 20 dB decrease in value of the, or magnitude of the output. Okay, so let's say for the sake of illustration, let's say if in this example you want to have cutoff frequency of 1 megahertz, given that C is 500 picofarad. So then it's not difficult to see that since you want omega C to be 1 megahertz, you would say um, 1 megahertz times 2 pi, because omega is 2 pi f. So 2 pi times 1 megahertz, that's your cutoff frequency of omega c, should be equal to 1 over R2, which is the unknown, this R2 that we had here, times C, which is 500 picofarad, which is 500 10 to the minus 12. Okay, so from here, the only unknown is R2, and you can figure out R2. Okay. In this case, obviously, R2 is not hard to find because it is 2 times 500, 1000, and then 1 meg with this one is 10 to the minus 6, and then you end up with 10 to the minus 3, it's 10 to the 3 divided by pi. So you're talking about R2 roughly 330 ohm or something on that order in order to get to the 1 megahertz cutoff frequency that you're interested in. One last point about intuitive understanding of how this first order 3 op-amp based circuit is working. Let's say just intuitively without even writing this transfer function, you want to figure out this whole system is low pass filter. So at super low frequencies, 1 over Cs, when S, which is a function of omega, becomes 0, this cap becomes open circuit. So this wire is actually open. And as a result of that, the output voltage is can be anything. And you can see that um, given this loop here, so you can see that effectively what happens is V out becomes equal to Vin. Now at super high frequencies, S goes to infinity, and as a result of that, this is short. Because this is short, then this op-amp becomes effectively a buffer because it is purely connection of negative terminal to the output, and then negative terminal should be equal to positive terminal, which is 0. So 0 is forced at the output at super high frequencies, no matter what the value of Vn is. Therefore, output becomes 0 at high enough frequencies, so it's not passing anything at high enough frequencies. Therefore, this is a low pass filter. Um, just wanted to further highlight that uh, as you can see in this system, this is just one realization of first order low pass Butterworth filter. Of course, there are many other ways to realize it, but this is one practical way of doing it. There are other complications involved in terms of sensitivity analysis as a function of resistors here. One nice thing about the setup of resistors here is as long as you can see they are all matching, so you're using the same resistor, that in practice reduces the problem of mismatch in the value of resistors. So that is also helpful. Okay, I hope that you find this helpful. Thank you.